Hi class, welcome to the presentation on Chapter 9, The Conquest of Infectious Diseases. Now this chapter will focus on diseases that through public health efforts we have either drastically reduced the numbers, and in at least one case we've completely eradicated one of these infectious diseases that once caused huge numbers of deaths around the world. The next chapter, Chapter 10, we'll look at more emerging infectious diseases, ones that we're currently battling like COVID-19, but this chapter looks at more historical illnesses. So in the grand scheme of history, it was only until recently that infectious diseases were the major killer of humans. And you've likely heard of the things on the screen right here: bubonic plague, tuberculosis, smallpox, cholera, and the others. But really, other than the flu, how many people have you known to have these other illnesses? Now, when I think of bubonic plague, I think of a more Victorian era illness. And as you can see from the drawing on the right, this was the plague in 1665 in London that caused thousands upon thousands of deaths. Even though it sounds like something from the past, people do still get plague. We have a few cases every year out in the western portion of the United States, so it does still happen. Now, when I worked at the health department in Mississippi, we would learn of the occasional case of tuberculosis, mostly in HIV-infected patients, but not always. We would have cases of tuberculosis, but through the administration of antibiotics, this condition in those people generally went away. Now, that's not to say that humans don't still get these conditions, because around the world, many of these illnesses persist. Now, keep in mind there is the exception of smallpox. Now, you probably haven't heard a lot about this because I'm certain that most of you were born in the last 20 or 25 years, and the last case was diagnosed in October of 1977. And through a massive vaccination effort, it was certified as globally eradicated, meaning it's not found in the wild at all anymore. It was considered eradicated by the World Health Organization in 1980. So really, we don't have to worry about smallpox anymore. There are two places that it exists, and they are at the CDC and a lab in Russia. And they hold on to these in case a vaccine ever had to be developed again. Hopefully it won't. Now, despite what we've been through and continue to be going through with COVID-19, we're actually quite lucky to live in an era where infectious diseases are considered quite innocuous. Now, through immunization campaigns and the discovery and continued development and use of antibiotics and other public health measures like purification of water, proper sewage disposal techniques, milk pasteurization, and improved nutrition and personal hygiene, we basically conquered many of the infectious diseases that were just mentioned on the slide before. And most of you have probably taken biology or microbiology, even in college, and are well aware that infectious diseases that produce epidemics are caused usually by bacteria, viruses, and parasites. And you can see examples of this, of each of those on this slide. Now, before the late 1800s, people thought all kinds of things, that foul smells, witchcraft, their sins, and even spontaneous generation could cause disease. That was until 1861. And I'm sure you've all heard of Louis Pasteur, whom pasteurization was named after. He developed the germ theory, leading the way to a very important discovery of various disease-causing bacteria. And in 1884, a man named Robert Koch, who you see on this slide, set out to determine what was the underlying reason that sheep and cattle were dying at high rates from anthrax. Now, he ultimately was able to grow, isolate, and prove that anthrax bacilli was the cause of anthrax, and through his bacteriological studies developed a set of rules or postulates that could be used to show that a specific microorganism caused a particular disease. Now, you've heard of these rules called Koch's postulates and are quite straightforward now, but at the time the concept of bacterial classification was novel. Now, his postulates were that number one, the organism must be present in every case of a disease. For example, each animal with anthrax symptoms had to actually have contracted the disease through the bacterium Bacillus anthracis. The organism must then be able to be isolated and grown in the laboratory. Third, when an animal is injected with the lab-grown culture, they must develop the disease. And finally, the organism must be able to be isolated from the newly infected animal. From here, the process should be repeatable. He was ultimately able to use these postulates to prove that tubercle bacilli were the cause of tuberculosis and Vibrio cholera the cause of cholera. Now, the organism that causes tuberculosis is now known as Mycobacterium tuberculosis. That's just a side note in case you've studied about that before. And we all know that infectious diseases are transmitted through direct methods, such as from one person to another, or they can be indirectly transmitted from food, water, or vectors, such as insects and animals. Now, when I did work at the health department, I was a restaurant health inspector for the state of Mississippi, and I was able to firsthand see how quickly bacteria and viruses were spread through food and water. Often these organisms proliferated in foods because leftovers were not cooled appropriately or stored at the right temperatures, causing the organisms to multiply at a rapid rate. Sadly, we also had a hepatitis A outbreak found to be caused by fecally contaminated produce. It was an employee who unknowingly was carrying the hepatitis A virus. He did not wash his hands appropriately after using the bathroom, then cut produce, thereby passing the virus on to others in my county where I worked. He was a carrier of the virus, meaning he had no symptoms but was still shedding the virus. Another infamous example of a healthy disease carrier was Typhoid Mary, a woman who spread typhoid fever in the early 20th century, even though she showed no symptoms of disease. I've provided an interesting video on Mary Mallon, who was Typhoid Mary, within the chapter material on the Blackboard site. And I put on the screen a picture of ice cream because it was found that the way that she was passing typhoid on to others was through her famous peach ice cream recipe, where she would cut fresh peaches and mix them into ice cream. And that's how the typhoid was actually passed from her hands into the food and then after consumption by others. So public health measures aim to break the chain of infection, to curb or even prevent an infectious disease outbreak. If you can interrupt the chain at certain points, transmission can be stopped. So let's briefly look at the chain of infection as shown on this slide. It obviously starts with a pathogen or the disease organism, the disease-causing organism, which, as I mentioned, is a bacteria, virus, or parasite that causes human disease. The reservoir is where the pathogen actually lives and can proliferate, which means survive and multiply. Now, for some organisms, the reservoir is human and only human, and for some, it's both animals and humans. And your book gives a few examples of zoonotic diseases, which are those that can be transmitted from animal reservoirs to humans, and those include things like rabies, bubonic plague, and salmonellosis. Now, a lot of you are studying veterinary medicine, and I know these kinds of illnesses are, in particular, interesting to you. So let's move on. The organism must have an escape from the reservoir to infect a new host. For example, a bite from a flea or mosquito can transmit, or through respiratory droplets. And even then, the new host must be susceptible. Some hosts may be immune to the pathogen, or the host may not be susceptible at all. For instance, the human immune system is very well equipped to attack the larval form of heartworms that we see in dogs. This is why we don't get heartworms as humans. In other words, we're just not good hosts for this parasite, so the chain is broken at that point. Now, keep in mind the chain of infection can be broken at whichever link is the most vulnerable for a particular pathogen. And since I studied pathogenic E. coli in my doctoral research, that's what I chose to focus on in this example. Now, E. coli can be destroyed through thorough cooking in a food product, breaking the chain at link 1. Link 2 could be broken by destroying contaminated meat at the processing facility before it gets to the consumer. Beef, for instance, at the processing facility, after the beef cattle are slaughtered, it is randomly tested. There are random samples that they test to see if E. coli from the intestines of the cattle have spilled onto the actual portion that will be packed as edible meat. So if that is found, if there are certain numbers of E. coli found, in particular pathogenic E. coli, that meat cannot go on to the to be processed for consumption. That's why you often see a lot of recalls for meat. It's because somehow E. coli was missed, was consumed by consumers after they purchased it at the store, and then they got sick. And that's how we can link it back to certain processing facilities usually. So then hand washing after handling raw meat could break the chain at link 3 by blocking the mode of escape if it is, in fact, on your hands. So there are many ways to break the chain of infection. Now, we learned about epidemiologic surveillance in Chapter 4 and how important it is in helping to interrupt the chain of infection. When an outbreak is detected through surveillance, there are several public health measures that can be taken. Now, interestingly enough, we've seen all of these measures taken during the global COVID-19 pandemic, including contact tracing, where those who have come in contact with an infected individual are notified of their exposure. Now, I've seen much of this in my daughter's schools, where a student tests positive for COVID and the school must contact trace or determine which students have had exposure to the positive case. Thus, they will notify these people as soon as possible. These students are then asked to quarantine for 10 days to prevent further spread of the virus. Now that several companies have released vaccines for COVID, there's hope this will also curb the spread of the virus. The classic public health measures of contact tracing, immunization, and quarantine are routinely used for a variety of diseases, including the ones in your book that are discussed, like SARS and rabies. And you will need to go ahead and read about those, although I'm not discussing them right now. So I personally find disease eradication fascinating because of the sheer effort that goes into it. If there is no non-human reservoir, and if a vaccine exists, entire diseases can be eradicated. And I mentioned this at the beginning of the presentation, but a great example of this is the eradication of smallpox. Again, that was in 1977. It was a highly contagious disease spread by touch or through aerosol droplets and claimed many lives until inoculation began to occur. And in fact, the concept of vaccination began with smallpox, and I have included a really interesting short video about the eradication of smallpox within our Blackboard material that you need to view. Polio is another illness that's been eradicated from the Western Hemisphere, but unfortunately, cases are on the rise around the world, and I've provided a brief article to read on this very topic, also within our Blackboard material, so be sure to read it. Measles is the next target for eradication, although no longer considered endemic in the U.S. because of the measles, mumps, and rubella, or MMR vaccine. Cases have been on the rise due to many parents choosing not to vaccinate their children, and that is an entire other lecture that we could have. Everybody has an opinion on this. Now, of all the new measles cases in 2019, 90% were found in unvaccinated people. We've also seen cases rise in the past because of relaxed public health measures. For instance, we thought that once we were vaccinated for measles, we were protected. It was soon found that after a while, our immunity waned and vaccination boosters were needed to increase immunity. And if you don't get the booster, then you are no longer protected from measles. Now, most of us are well aware of the benefits of vaccines, and I'm sure most of you are vaccinated. But in the late 1990s, rumors were spread that vaccines caused autism and sudden infant death syndrome, otherwise known as SIDS. Andrew Wakefield was a British surgeon who published a research paper in a fairly prestigious journal called The Lancet that supposedly linked vaccines with autism. Further study and investigations found his claims to be fraudulent, and the paper was retracted. First of all, there were only, I believe, fewer than 20 people in the study, which makes the validity quite low anyway. But it was found that he was scheming to profit through filing lawsuits against manufacturers of vaccines. In the meantime, though, celebrity endorsements of the theory spread this information like wildfire. And I remember all of this happening. And even today, more than 20 years later, parental concern over vaccines still exists. Now, the issue with this is that if many people do not get vaccinated, we lose our herd immunity, which is the protection from a disease afforded by a high rate of immunization. Now, herd immunity is extremely important for infants who are too young to receive vaccines or people with weakened immune systems. And if we lose it, these people are at very high risk of contracting certain very preventable illnesses, like measles, for instance. Now, some pharmaceutical companies are reluctant to develop new vaccines altogether due to low profits and risk of lawsuits, which it's sad that we do have a very sue-happy society, but that's one of the reasons that new vaccines are slow to develop, unfortunately. Now, that was a quick overview of the material in Chapter 9. If you have any questions or comments, feel free to contact me via email directly or post your questions in the virtual discussion board within the Blackboard site. If you, as usual, if you have a comment that you want to make just to me, please email me because the discussion boards are visible to everybody. But otherwise, questions posted on there are often quite helpful to others in the class. Again, hope you have a good day, and if you need anything, just contact me.